Electrometallurgy. Under electrometallurgy, we are going to learn extraction of aluminum and extraction of magnesium. See, electrometallurgy is applied to those metals which are highly active, which cannot be reduced easily carbon. For such metals, we apply electrometallurgy. Active metals like metals of group 1A, group 2A, even aluminum, electrometallurgy is applied. Here we pass current through an molten electrolyte. We pass current through molten electrolyte and we extract the metal. The metal is formed at cathode. Let's learn electrometallurgy with the help of these two examples, extraction of aluminum and extraction of magnesium. Let's start with extraction of aluminum. First of all, I'd like to give you list of important ores of aluminum, then we'll look into extraction of aluminum from bauxite. The list of important minerals of aluminum. A. Corundum. Corundum is Al2O3. Diaspore. Diaspore is Al2O3 dot H2O. Next, bauxite. Bauxite is Al2O3 dot 2H2O. Next, gypsite. This is Al2O3 dot 3H2O. Next, you have cryolite. Cryolite is Na3AlF6. This is a double salt, a double fluoride made up of AlF3 dot 3NAF. This is the composition of cryolite. F. Feldspar. It is a silicate mineral, KAlSi3O8. This is feldspar. Kaolin. Al2O3 dot SiO2 dot H2O. These are few important minerals of aluminum, and the most important mineral is bauxite. I would like to add one more. Turquoise. Turquoise is AlPO4 dot Al2O3 dot H2O. It's a phosphate mineral of aluminum. Turquoise, AlPO4 dot Al2O3 dot H2O. So this is an important list of important minerals of aluminum, and the chief ore. Aluminum is mainly extracted from bauxite mineral. Bauxite is a dihydrate of Al2O3. Let's learn extraction of aluminum from bauxite. Let's now learn extraction of aluminum from bauxite ore. Bauxite ore is bauxite ore consists of Al2O3 dot 2H2O. This is the chemical composition of bauxite. Apart from this, it is associated with impurities. There are two types of impurities associated with bauxite, and based on that, bauxite is given two different names. You have white bauxite and red bauxite. White bauxite, red bauxite. White bauxite consists of SiO2 impurity, and red bauxite consists of iron oxide impurity. So bauxite associated with silica impurity is called as white bauxite, and the bauxite which is associated with iron oxide impurity is called as red bauxite. So the very first step in the extraction of aluminum from bauxite is the purification of bauxite. So important stages in the extraction of aluminum are: number one is purification of bauxite. Number 2 is electrolytic reduction. This is the reduction stage. Electrolytic reduction of Al2O3 alumina, and the last and final stage is purification of aluminium. Purification of or refining of aluminium. So these are the 3 stages in the extraction of aluminium: purification of bauxite, electrolytic reduction of alumina, and then purification of aluminium. As I told you, bauxite is of 2 types, white and red bauxite. So the method of purification of bauxite depends upon whether the bauxite is red bauxite or white bauxite. Let's discuss first of all purification of bauxite, the various methods of purification of bauxite. Now the first stage, purification of bauxite. Here we have 3 different methods available. A, Bayer's process. B, Hall's process. And C, Serpek's process. These are the 3 different methods available for the concentration of bauxite or purification of bauxite: Bayer's process, Hall's process, and Serpek's process. Remember, Bayer's and Hall's process are meant for purification of red bauxite. Serpek's process purifies white bauxite. Serpek's process is for white bauxite. Bayer's and Hall's process are for red bauxite. So we'll first talk about Bayer's process, then we'll talk about Hall's process and Serpek's process. I will show you with the help of this flow chart. Al2O3.2H2O plus iron oxide impurity. This is the impurity. This is first heated. When you heat it, Al2O3, heat it in presence of air, then most of the bauxite will lose water of crystallization and iron oxide becomes Fe2O3. Actually, here you have a mixture of ferric oxide, mostly ferric oxide, and some ferrous oxide. So during this process, all the ferrous oxide will get oxidized to ferric oxide. The idea is to transform more basic oxide into a less basic oxide, Fe2O3. Now, what we need to do is add sodium hydroxide and heat the solution at 423 Kelvin in an autoclave. Add sodium hydroxide to this mixture in an autoclave, heat it to 423 Kelvin. Then you get NaAlO2 and Fe2O3. Then you need to, this is soluble, this is insoluble. Do the filtration. On filtration, you have NaAlO2 in your hand. Fe2O3 is removed as a residue. Now, add water and a crystal of aluminum hydroxide. This will act as a seeding agent. It is called as seeding. This will initiate crystallization of the substance. So you get AlOH taken thrice, precipitate. Then this is subjected to ignition, sudden heating to high temperature. Then it will lose water and you get. So ignition of AlOH taken thrice gives Al2O3. It will lose water. So in this way, you get Al2O3 free from iron oxide impurities. This is Bayer's process of concentration of purification of bauxite. I'll repeat once again. Bauxite is Al2O3.2H2O with iron oxide impurities. It is first heated in presence of air so that all the ferrous oxide becomes ferric oxide. Now you add sodium hydroxide. This being amphoteric in nature will dissolve in sodium hydroxide to give NaAlO2, sodium meta-aluminate, whereas Fe2O3 is unaffected. It remains as it is. Now we do filtration to get rid of Fe2O3. At this stage, Fe2O3 is lost. and then what we have is soluble substance NaAlO2. This is then mixed with lots of water, and you add a crystal of aluminum hydroxide which acts as a seeding agent, and you get precipitate of aluminum hydroxide. This is then subjected to ignition. After filtration, it is subjected to ignition and you get anhydrous alumina. Let's now learn another method of concentration of bauxite, that is Hall's process. See, in the base process, the separating agent we have used is sodium hydroxide solution, whereas in Hall's process we make use of sodium carbonate solution. So that is the basic difference between Bayer's process and Hall's process. In Bayer's process we use sodium hydroxide, in Hall's process we use sodium carbonate. So it's a similar type of technique, Al2O3 dot H2O to H2O. Apart from that, we have iron oxide associated as an impurity. This is heated in air and you get Al2O3 plus Fe2O3, and then this is then treated with sodium carbonate solution. Then you get NaAlO2 plus carbon dioxide gas is produced, Fe2O3 remains as it is. This is removed by filtration. Now you do filtration, you get rid of Fe2O3 minus, minus Fe2O3. Now what you have in your hands now is NaAlO2. This is then diluted with water and carbon dioxide gas is bubbled. You get AlOH taken thrice, which is insoluble, and a soluble substance Na2CO3. Again you do filtration. On filtration you get aluminum hydroxide solid. This is subjected to ignition to get Al2O3. So this method is quite similar to Bayer's technique, only difference is use of sodium carbonate instead of sodium hydroxide. Rest of the things are all similar. The next method we are going to discuss regarding concentration of bauxite is C, that is Serpek's process. Serpek's process is meant for the purification of white bauxite. White bauxite consists of SiO2 impurity. Remember, what you have in your hand is Al2O3 dot 2H2O, which is contaminated with SiO2. Our job is to get rid of SiO2. Now, what we do here is we mix the powdered bauxite ore with coke and heat it in an atmosphere of nitrogen gas. Powdered ore is mixed with coke and heated in an atmosphere of nitrogen gas at about 1800 degrees Celsius. When you do this, SiO2 impurity is also there, please don't forget that. So coke, you have SiO2 also. This is your impurity. Coke will transform SiO2 to Si, which escapes out as volatile fumes. Coke itself will get oxidized to carbon monoxide, which also escapes out as a gas. Al2O3 also will be reduced to Al, and then subsequently it reacts with nitrogen and you get ALN. These two are volatile substances, they escape out. What is left out at the end is ALN, called as aluminium nitride. Now, I'll repeat. The powdered ore containing SiO2 impurity is mixed with coke and it is heated to 1800 degrees Celsius in an atmosphere of nitrogen gas. Coke will reduce both SiO2 and Al2O3. SiO2 is reduced to Si, it escapes out as volatile fumes. Al2O3 after reduction will get a chance to react with nitrogen to become ALN. ALN is left out, carbon monoxide and Si escape out. Now, ALN is then treated with steam. Hydrolysis takes place and you get AlOH taken thrice, ammonia gas escapes out. This on ignition gives rise to Al2O3. This is the process called as Serpek's process. We lose silica as silicon. The next stage in the extraction of aluminum is the electrolytic reduction of alumina. Electrolytic reduction of alumina. See, the biggest problem with alumina is its high melting point. It melts at a very high temperature, somewhere around 3000 degrees Celsius. Another big problem with alumina is it's a bad conductor of electricity. To overcome these two problems, that is high melting point and bad conducting nature of alumina, we mix alumina with cryolite. Cryolite is Na3AlF6. So, this will take care of two problems, both the problems of alumina, that is its high melting point and its bad conducting nature. So, that is the reason why cryolite is added. This acts as a flux, right? And then we use carbon rods as anode and the iron tank itself will act as cathode. Iron tank itself acts as cathode and the carbon rods which are suspended from above act as anode. And due to addition of cryolite, the melting fusion temperature comes down to 900 degrees Celsius. This is the temperature maintained to keep these two substances in the molten state. Now, and here we have powdered coke. This will prevent aerial oxidation of the substance. So, this is the setup. Now, let us see the reactions which take place during electrolysis. Na3AlF6, it breaks up into AlF3 and 3NAF. AlF3 then dissociates into Al3 plus and F minus. At anode, F minus loses electrons, gets oxidized to fluorine, and this F2 will immediately combine with Al2O3 to produce, again it will regenerate AlF3 and O2 is given out. This O2 will attack carbon of the anode and what comes out is a mixture of carbon monoxide and carbon dioxide. So, anode is burnt off in this process. Now, what happens at cathode? At cathode, Al3 plus picks up 3 electrons and becomes aluminium metal. This aluminium being heavier will reach the bottom and it can be recovered from the outlet which is provided at the bottom. So, the products of electrolysis are aluminium is formed at cathode and at anode oxygen is produced which later will oxidize the anode to carbon monoxide and carbon dioxide. Mostly carbon monoxide is formed. In this way, anode has to be constantly replaced. Last stage in the extraction of aluminium is purification of aluminium. The method we are going to discuss is called Hoops process. This is also an electrolytic process. Here we have 3 layers of fused masses. They differ in their specific gravities, that's why they are in 3 layers. The bottom layer is impure aluminium. The middle layer consists of electrolyte. This is cryolite and potassium fluoride is also added to maintain the specific gravity. And then this is a layer of pure aluminium. Dipping in this layer we have carbon rods which act as cathode, and the impure aluminium carbon rod is present which acts as anode. Well, here we have an arrangement for tapping out pure aluminium through this outlet. And this is a funnel with a long stem provided. so that you can directly introduce impure aluminum to the bottom layer without disturbing the first two layers. Now, when you pass current into this, impure aluminum gets oxidized to Al3 plus and enters into this compartment. Al3 plus from this compartment, the middle layer, will enter into the top layer, gets reduced as Al. So, the reactions are like this. At anode, Al becomes Al3 plus by losing 3 electrons. This happens in the bottom layer. Al becomes Al3 plus and enters into the middle layer. Now, at cathode, that is the top layer, at cathode, Al3 plus from the middle layer picks up 3 electrons and becomes Al and forms a part of top layer. So, as time goes, the level of the bottom layer decreases and the level of top layer increases. When sufficient amount of aluminum is formed in the top layer, we have a tapping hole outlet through which pure aluminum can be recovered. This gives highly pure aluminum. Under electrometallurgy, the next extraction is, after aluminum, we are learning extraction of magnesium. Extraction of magnesium, this also comes under electrometallurgy. Because magnesium is highly electropositive, so we cannot go for carbon reduction. That will become highly expensive. So, electrometallurgy is applicable. Electrolysis of fused magnesium salt is done to extract magnesium. First of all, I will give the list of important minerals of magnesium. Important sources or important minerals of magnesium. A, you have magnesite. Magnesite is MgCO3, and B, dolomite. Dolomite is MgCO3.CaCO3. C, carnallite. Carnallite is KCl MgCl2 6H2O. It is a double salt, double chloride of potassium and magnesium. Then another important source of magnesium is seawater. Seawater contains soluble salt of magnesium. So, these are the important sources of magnesium, and we will see how magnesium is extracted from these three sources. Number 1, magnesite, number 2, carnallite, and number 3 is seawater. Let us see how magnesium is extracted from these sources. A, from magnesite. Magnesite is MgCO3. MgCO3 is heated, it decomposes to give magnesium oxide. Carbon dioxide escapes out. Then this is mixed with coke and heated in a current of chlorine gas. You get magnesium chloride. This is subjected to electrolysis. You get magnesium and chlorine. I will elaborate this after some time. So, this is how magnesium is extracted from magnesite. Magnesite is heated to get magnesium oxide. Magnesium oxide is mixed with coke and heated in a current of chlorine gas. You get magnesium chloride. Magnesium chloride is then subjected to electrolysis and you get magnesium at cathode, chlorine at anode. This is formed at cathode. This is formed at anode, but I will elaborate on this after some time. Now, let us see how magnesium is extracted from carnallite. Carnallite is KCl MgCl2.6H2O. The very first thing you need to do is remove this water of crystallization. So, heat carnallite to about 175 degrees Celsius, then it will lose 4 water molecules. You get KCl, MgCl2 dot 2H2O, dihydrate. You cannot remove these water molecules by further heating, because see, if you do that, then this will undergo hydrolysis. MgCl2 will undergo hydrolysis to give magnesium oxide. So what we need to do is heat it in presence of HCl gas. If you don't circulate HCl gas, then there is a possibility of MgCl2 undergoing hydrolysis to give MgO. Here you need to heat it to 350 degrees Celsius. You get anhydrous MgCl2. This is subjected to electrolysis to get magnesium at cathode and chlorine anode. So this is how carnallite is transformed into metallic magnesium. First we need to heat it to about 175 degrees Celsius. You get rid of 4 water molecules, then further heating is done in presence of HCl gas to avoid hydrolysis of MgCl2. Then you get anhydrous MgCl2, which is subjected to electrolysis in the fused state, and you get metallic magnesium. Let's now learn extraction of magnesium from seawater. To the seawater contains Mg2 plus ions. Seawater we add milk of lime. Milk of lime is a suspension of calcium hydroxide. So milk of lime is added to seawater. The magnesium ions present in seawater will react with OH to give insoluble substance MgOH taken twice. Magnesium hydroxide is formed. This is then treated with HCl. You get MgCl2 dot 6H2O. This is then heated in a current of HCl gas, and you get anhydrous magnesium chloride. This is then subjected to electrolysis, and you get magnesium at cathode and chlorine at anode. So I'll repeat the whole sequence. Seawater, which consists of magnesium ions, is treated with milk of lime, which is calcium hydroxide, and you get magnesium hydroxide. This is a soluble substance, this is insoluble. So it comes out as a precipitate. Recover this by filtration and then treat it with HCl. Then you get hexahydrate of magnesium chloride. This is heated in a current of HCl gas. I told you, if you don't use current of HCl gas, then there is a possibility of this undergoing hydrolysis. So you get anhydrous magnesium chloride on this, and then this is subjected to electrolysis, and you end up with magnesium at cathode and chlorine at anode. This is how magnesium is extracted from seawater. Now let us now discuss electrolysis, elaborate on this, electrolysis of magnesium chloride. This is regarding electrolytic reduction of MgCl2, electrolytic reduction of magnesium chloride. Let's see how it is done. We have a rectangular steel tank. The steel tank itself acts as cathode, you can see here. A graphite rod is suspended from above, which acts as anode, and we have a provision for circulation of coal gas, because the magnesium which is going to form in the electrolysis will float on the surface, and there is a possibility that it may undergo aerial oxidation, because the reaction is being performed at 700 degrees Celsius. At this temperature, there is a chance of magnesium combining with oxygen of air. So air inside is replaced by coal gas. Coal gas is constantly being circulated. This is to keep magnesium safe. Magnesium is floating on the surface. Unlike aluminum sinks to the bottom, whereas magnesium floats on the surface. A graphite rod acts as anode, as I told you. Anode is enclosed in a porcelain hood, because the gas which is going to form an anode is chlorine, and you have a provision, an outlet to flush out chlorine as soon as it is formed. It will not get a chance to combine with magnesium because of the porcelain hood. Electrolyte consists of molten magnesium chloride along with some sodium chloride, which increases conduction, and the temperature which is maintained here is 700 degrees Celsius. So I'll repeat things. First thing is, electrolytic vessel is a steel tank which is itself acting as cathode. A graphite rod acts as anode. Electrolyte consists of MgCl2 with some sodium chloride, and the temperature is 700 degrees Celsius. There is a provision for circulation of coal gas so that magnesium is not oxidized, and chlorine is formed at anode, and it comes out from an outlet provided on the hood. The hood is provided to prevent mixing of magnesium and chlorine, the products of electrolysis. Let us look at the reactions which take place during electrolysis. MgCl2 dissociates into Mg2 plus and Cl minus. At anode, Cl minus undergoes oxidation. Oxidation means loss of electrons. It becomes chlorine. It comes out through the outlet provided on the hood, and then at cathode, Mg2 plus picks up 2 electrons and forms magnesium. This is the reaction which takes place at cathode. Magnesium is formed at cathode, and it rises above and forms the upper layer.